Okay, we are coming to chapter 6, limits of sequences. Analysis is nothing but limits. Analysis is nothing but limits. All of them are limits. To an analyst, whole world is limits. Limits. There is nothing without limits. Without limits is algebra. Group theory, this sort of thing, no limits. Discrete. So compared to, it said it could be a false statement. Compared to analysis, algebra is easy. That may not be true. How can I say algebra is easy? But that's the way one feels because it is discrete. Here everything is continuous. Continuous. Okay, let's go through. In the previous chapter, we defined the real numbers as formal limits of rational Cauchy sequences, and we defined various operations of the real numbers. What we did was last chapter, if xn is a Cauchy sequence, we wrote capital Lim, n tends to infinity xn. We said that is a real number. That means every Cauchy sequence gives a real number. That's what it meant. However, unlike our work in constructing the integers, where we eventually replace formal differences with actual differences, and rationals, where we eventually replace formal quotients with actual quotients, we never really finished the job of constructing the real numbers because we never got around replacing formal limits with actual limits. Everything we replace, you said double line, division, we replace them with the actual one. Here we haven't done it. Actually, he says, in fact, we haven't defined limits at all yet. This will now be rectified. That's what he is saying. We begin by repeating much of the machinery of epsilon closed sequences, etc. Again, but this time we do it for sequences of real numbers. We have talked about epsilon closeness for rational sequences, but now we are going to do it for real sequences. Thus, this discussion will supersede what we did in the previous chapter. And we are passing that. Whatever we are doing will supersede that. That will be history. First, we define distance for real numbers. So, for the time being, however, according to the book and our knowledge, real numbers are nothing but formal limits of Cauchy rational sequences. That's all we know. Distance between two real numbers is usually dxy is absolute value of x minus y. Clearly, this definition is consistent with definition 4.3.2. I guess it must be for rational numbers, we have given the same definition. Further, proposition 4.3.3 works just as well for real numbers as it does for rationals because the real numbers obey the rules of algebra that the rationals do. We have proved all of them actually. Definition 6.1.2, epsilon closed real numbers. Again, usual one, let epsilon greater than 0 be a real number. We say that the two real numbers x, y are epsilon closed if and only if we have dyx less than or equal to epsilon. That means the distance between x and y is at the most epsilon. Again, it is clear that this definition of epsilon closed is consistent with definition 4.3.4, whether it is rational or real, distance mean the same thing. Now let a n be a sequence of real numbers, that is, we assign a real number a n for every integer n greater than or equal to n. He is talking about a sequence. Sequence means for every integer you give some number. That's all. If you begin from first integer, you call it a1, you give some number. For the second, you give a2, like that. The starting index m is some integer, usually this will be 1. But in some cases, we will start from some index other than 1. the choice of label used to index this sequence is unimportant. We could use, for instance, AKK going m to infinity, or else ANN going m to infinity. Same thing, no difference. Actually, we call it a dummy variable. It doesn't play any role, it's dummy. We can define the notion of a Cauchy sequence in the same manner as before. Cauchy sequence of reals. Let epsilon greater than 0 be a real number. The sequence AN, capital N to infinity, of real numbers starting at some integer, index n is said to be. And you see, by writing this sort of thing, making is useless. Yeah, it's more difficult for you because you are a beginner. When I write, I always begin from 1. It's easy for the student. No? After learning that, then you can start from anywhere because you know. No? Anyway, let's go. A sequence n going starting from capital N to infinity of real numbers is starting at some integer index capital N is said to be epsilon steady if and only if aj, ak are epsilon closed for every jk greater than or equal to n. So you need to remember that when he says epsilon is steady, that is for all the terms. At distance between any two terms of the sequence is at the most epsilon. A sequence A n going m to simple m to infinity starting at some index m is said to be eventually epsilon is steady if and only if there is an integer n greater than or equal to m such that a n going to infinity is epsilon steady. Eventually steady means you go somewhere far away, then from there onwards, all of them are at a distance at the most epsilon. That is the meaning of eventually epsilon steady. We say that a and n going m to infinity is Cauchy sequence if and only if it is eventually epsilon steady for every epsilon greater than 0. Actually, if you go to the university, that's the only definition you need. All these first 2, 3, 6 lines are redundant. You say a and n going from m to infinity is a Cauchy sequence. If it is, you don't use the word eventual, but same meaning. For every epsilon greater than 0, there is some integer. Let me write it. Shall I erase the board? No. So I also would like if you and I are at the same, when I say you means your homework, at the same level. Now you are doing chapter 4 homework, I am doing chapter 6. How can we catch up? Because before we finish this book, we should try all the problems. And we are not on par. I am somewhere, you are somewhere else. So what you need to remember is a sequence xn is writing, no, let me say n going 1 to infinity, is Cauchy. If for each epsilon greater than 0, this is what you need to remember. There is n belongs to Z class such that for each n greater than or greater than or equal to n, we have absolute value of a minus a less than epsilon. What it means is, if you draw a graph of, so now this, you are drawing here discrete graph. No, this is sequence. You have values of 1, 2, 3, 4, 5, then 5 is here, here. Let me do it even longer. Here, here, here. So at that very, this side is AN. X, Y axis, this is N. So maybe A1 is here, A2 is here, A3 is here, A4 is here, A5 is here. But if it is quotient, what it says is when you go far away, if you take any two of them, so after capital N, say let's say this here is capital N. Beyond capital N, if you take, say, let's say this is N, then this one is N plus 1. So assume N plus 1 is here. So if you take epsilon distance to either side and draw a little line, I mean dotted line, sorry. I say little line. Sometimes I say nonsense. No? Two dotted lines. This is AN. So all of them are graph must be in between these, no? Because you take anyone here, this one and distance between these two must be less than epsilon. So this is going to be in a kind of a little tube, all of them. It's like if you take a big, very long epsilon, not epsilon, epsilon. Epsilon by very small, all of them are going to be in the epsilon and epsilon are somewhat close should be in this pipe, all of them. It cannot be it cannot be like going this way. It cannot turn because anyone here, if you are going to turn the tube, epsilon this radius, because then this one and this one are much bigger than. So this is, all of them must be in a horizontal tube, far away, in a very small radius. So in other words, if you take a Cauchy sequence, if you are given epsilon, if you take epsilon tube, epsilon or whatever, you must be able to put all of them, depending on the radius of the epsilon tube, all of them will come to the tube after some point. That is the meaning of it is quotient. No matter which epsilon you choose, all of them will be in the tube eventually. At the beginning they are going up and down, here and there, but after all, at the end of the day, they all are going to be inside this epsilon radius tube inside. That is the meaning of quotient. That's the meaning of quotient. So very important here, no matter what epsilon you choose, there is an integer n. How? No matter which any two terms you choose, after n and capital N, distance between them is at the most epsilon. Again, right away, as a student, you need to know a sequence Xn according to this notation n going 1 to infinity is not quotient. You need to know that. But
if there exists epsilon greater than real,
there exists epsilon greater than 0, let me say epsilon 0 in that, not now. For the time being, let's go with epsilon 0. There exists epsilon greater than 0 such that
for each n belongs to Z plus,
for each capital N belongs to Z plus,
there exists n greater than n,
there exists n m greater than n such that
Mod A minus A is greater than or equal to
mod A minus mod A greater than or equal to epsilon. Very good. Correct, no? So, up to that level, you are good. Up to that level, you are, no, some people cannot say this.
So
Yeah, some people. Yes,
in this book, epsilon an minus am mod is larger than epsilon, right?
Ready?
In this book, we say it's Cauchy when an minus am mod is smaller than or equal epsilon.
That doesn't matter. It doesn't matter. Whether you write less than or equal or it doesn't play any role because we can prove it also. Let's prove it next day, not today. Whether having less than or equal or having less than it doesn't make any difference. You say the book says less than or equal. Yeah, he says epsilon is still occasionally equal. You are right. Anyway, let's prove it next day. But many authors is redundant. They put strict less than epsilon to give the impression that when you say equal kind of distance maintains, somebody may think A minus A is at a distant epsilon. When you write epsilon, no matter which epsilon you use, is strictly less than that. Is a better way, but doesn't matter whether you write this way. If you write that way, then here it could be again greater, but again it doesn't matter. But good point, good student, even though he came empty-handed from the trip. So now, again, even though I see the thing is here he is jumping, I don't want to jump because you are behind the homework, so let's do something. No? Let's prove. Very easy, two exercises. You need to learn to prove because prove. Show that. The sequence Xn given by Xn is equal to 10 for each n belongs to n is Cauchy. Very simple exercise. By doing very simple exercises, you learn how to write proofs. Proof. So if you want to prove, this is the definition. What should be my first statement of the proof?
epsilon be larger.
You said?
Let epsilon greater than 0.
Let epsilon greater than 0 be arbitrary. Very good. Now in your head you know that you need a capital N belongs to Z plus with the property that A n minus A m less than or equal to epsilon. So rough work. You get A n minus A m, you check A n is 10, A m is also 10, 10 minus 10 is 10, absolute value 0 is equal to 0. Now you know 0 less than epsilon for always. Therefore, Uta, who came empty-handed, what is my capital A? Let or put whatever the word you like, put n equals.
Anything?
You tell me the number. I gave you the chance.
1.
1 is too nice. 18 because you are 18 years old. Then n is equal to 18. Then 18 belongs to Z plus and for each nm greater than 18, what is the sequence? Xn. Xn minus Xm is 10 minus 10 less than 0. We have to read thus. Limit n tends to infinity. Xn is equal to 10. This is very important. This one says if you take the constant sequence, it is limit, it converges and no, not converges here, it is quotient. We haven't reached the convergence part yet. It is quotient. Any constant sequence is quotient. Something else that I am not going to write. Any sequence which is eventually constant is also quotient, because you don't have to have the constant at the very beginning. Even if you write xn equals 10, another, if you take another sequence, say xn is equal to n for each n less than or equal to 10 to the 1000, so 1000 and less than or equal to 1. Then after 18, n strictly greater than 10 to the 1000. So this sequence is eventually constant after 10 to the 1000, and this is also quotient, right? So I am doing this thing, you need to, your hand must be flexible. Right now, he drives, so somebody who drives every day, driving will be, normal thing. But somebody who is learning, it is a very serious business. Okay, now we proved this sequence is quotient. Now, shall I guess? Like that, you always, you are reading the book, because I can do it, but according to Dr. Rabat, he also is issue. So I don't have that much time to go through these little things. Now, let me say, show that the sequence xn n going on to infinity given by xn equals minus 1 to the n for each n belongs to n is not for each n belongs to I write n and z plus simultaneous for each n belongs to z plus is not quotient. Proof. Get to the habit of proving little things. Then it will teach you how to write bigger proofs. Like this one, he asked me, how did I think about this? This is not my proof, this is a standard proof, even to students. But to think like this, you must be having the experience of writing little proofs. Especially if you are going to do a PhD in analysis. Yeah, you must be an expert in epsilon and there is both. Okay, so that the sequence of this thing is not quotient. Okay, yes, we want to prove that this sequence is not quotient. Actually, this is the sequence minus 1 plus 1 minus 1 plus 1 and so on. So, what is the sequence xn not quotient? If there is epsilon greater than 0. So, what should be the first sign of this proof?
Let epsilon.
Very good, very good. Let epsilon equals how much you take. So if you draw the graph, here I don't do that job, no, and I behave like non-analysis lecturer in this class. Here the graph is 1, 2, 3, 4, 5, 6, minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. That continues, that's the graph. So I want to show that this is not Cauchy. What is your epsilon?
1.
1. Then epsilon greater than. Actually, that's why I like to put this way. Because direct is no, it is a particular one, not arbitrary. So let's put it this way. Other things are, I say have this. Okay, then epsilon 0 greater than 0. Now what do you say? Then what am I going to write? Yeah, I'm group. What is the next line in my group?
For all n belongs to Z plus.
No, that's not English, no. It should be the English statement. You cannot start the English statement for all. What about you?
I can see what's going to happen. But
No, according to here, this, no. It's this. There is epsilon greater than 0. He said, it very well, it is correct. Then I wrote this part because that's what it says. I said for each n belongs to Z pass. So what should I write then?
let n belong to Z plus be arbitrary.
Let n belongs to Z plus be arbitrary. You are reading about?
Yeah, it's not important. So observe that n plus 1 and n plus 2 is greater than n.
Observe that n plus 1, n plus 2, they are greater than n, and
minus 1 to the power n plus
xn plus 1 minus xn plus 2 is here is minus 1 to the n plus 1 minus 1 to the n plus 1 plus 1, no?
Yeah.
N plus 2. Here minus 1 to the n plus 1 is common. Right? I take that out and I take that here, I will get 1. Here I will get minus 1 to the 1. This one is 1. Next one is 2. 1 times 2 is greater than epsilon 0. Because what we took epsilon 0, this Sudha gave this one. Then I wrote epsilon greater than 0. Aditya Buddha gave me, told me according to here, for each n belongs to Z plus. That's why he said, let Z plus n belongs to Z plus be arbitrary. For each n belongs to Z plus. He said, there is nm greater than n. He has chosen 2 of them greater than n. And he took actually 2 consecutive ones. Then xn plus 1 minus xn plus 2 minus 1 to the n plus 1 minus 1 to the n plus 1 plus 1. So I took minus 1 to the n plus 1 out. Then here you get 1. Then here you get minus 1 to the 1 minus is 2. This is 1 times 2 greater than epsilon 0. Hence, this sequence is not Cauchy. I mean, this is no big deal, but you need to be able to write logically and orderly, precisely. It's very important. Because if you cannot prove such a little thing, then how can you prove big things? That's the thing. So I can say that roughly all three are good, somewhat good in, you are good, very good in, I guess, logic part. You are also good. He is on the way, he is getting better. And next time he will bring something for us also, if he goes on a trip. Yeah, I'm always coming after him, no? Anyway, value, so when you say, even though there are many lines in this definition, this is the most important part. A sequence section is Cauchy if for each epsilon greater than 0, there is an integer n such that for each n greater than n, we have an minus n less than epsilon. I am not saying other parts are useless, but the last line is that we say that a and n going from m to infinity is Cauchy if and only if it is eventually Cauchy. Eventually epsilon is steady for every epsilon. What it means is no matter what epsilon you use, there is an integer capital N. After that, it is epsilon is steady. That means after any nm greater than capital N, xn minus a n minus am is less than epsilon. So by writing these many things, I get sometimes I don't know. Sometimes maybe students get little annoyed or confused or something. Many statements. No? Okay, to put it another way, a sequence xn of real numbers is a co-sequence for all real epsilon greater than 0, there is an integer n greater than or equal to m such that, so now he is writing what I said. These definitions are consistent with the corresponding definitions for rational numbers. I mean, it's obvious, although verifying consistency of co-sequences takes a little bit of care, he says. There is a little bit of a thing, because when you have talking about, let's say, n will be a sequence of rational numbers starting at some index m. n going m2 is a co-sequence in the sense of definition 5.1.8. Over there, that epsilon was rational. That's the difference. If you go to definition 5.1.8, let me go very quickly, just to tell you, 5.1.8. He says a sequence an of rational numbers is said to be a co-sequence if and only for every rational epsilon greater than 0. Here, no, it's not a requirement here. You see the difference? Over there, epsilon is rational, over here it is real number. Can be rational also. I mean, it's redundant here. Okay, so he wants to prove this by taking that definition is consistent with this one. Then he take let A be a sequence of rational numbers starting at some index n. Then A is a co-sequence in the sense of definition 5.1.8. That means epsilon is rational. If and only if it is a co-sequence in the sense of definition 6.1.3, that means epsilon is real. Proof. Suppose first that a n going from m to infinity is a co-sequence in the sense of definition 6.1.3. Then it is eventually epsilon is steady for every real epsilon greater than 0. It is true for any real epsilon, since any real rational number is real. In particular, it is eventually epsilon is steady for every rational. No, every rational number is real. No? So, which makes it a co-sequence in the sense of definition 5.1.8. So, if it is Cauchy under the 6.1.3, then it is Cauchy under whatever 5.1.8. That means if it is Cauchy when epsilon is real, then it is Cauchy when epsilon is rational. Now, other part is not that obvious. Now, suppose A is a Cauchy sequence in the sense of definition 5.1.8. Then it is eventually epsilon for every rational epsilon greater than 0. If now we have to prove that if it is true, definition says it is true when for every rational number. Now we have to prove it is true for every real number. If epsilon greater than 0 is a real number, I have to show that it works. Then there is a rational epsilon greater than 0 which is smaller than epsilon. I have told you this thing is a very important result. Let me again go back to 5.4.12. I have told you several times this is an important result. This is on page 114. It said, let x be a positive real number, then there exists a positive rational number q, such that q less than or equal to x. I have told you this is an important result, always. Maybe I have told you now several times. And there exists a positive integer n, such that x less than or equal to n. So, given any real number, there is a smaller rational number. That's what it says. If epsilon greater than 0 is a real number, then there exists a rational epsilon greater than 0, which is smaller than epsilon. What's the rational number? So, which is smaller than epsilon by proposition whatever 5.4.12. Since epsilon dash is rational, we know that an is eventually epsilon dash is steady. Since epsilon less than epsilon, this implies an is eventually epsilon is steady. Since epsilon is an arbitrary positive real number, we thus see that an is a Cauchy sequence in the sense of definition 6.1.3. Did you understand the proof? You want me to? No. Understand? So, I mean, if epsilon being rational or irrational do not play any role at all. But that result is very important. I mean, sooner or later you can prove them very easily, but for the time being, no. I say this. Yeah. Okay, then we come to, because of this proposition, we will no longer care about the distinction between definition 5.1.8 and 6.1.3 and we use the concept of a Cauchy sequence as a single unified concept. Now we talk about it means for a sequence of real numbers to converge to some limit L. That's, I told you, analysis is nothing but limits. Limits are nothing but analysis. Convergence of sequences. Let epsilon greater than 0 be a real number and let capital L be a real number. The sequence starting from capital N of real numbers is said to be epsilon close to L. If and only if n is epsilon close to L for every n greater than or equal to n. That is, we have mod of n minus L less than or equal to epsilon. For all n greater than or equal to. That's the meaning of it according to him. A real number, the sequence is epsilon close to L. All the terms are at the most epsilon distance from L. That's what it means. We say that the sequence an is eventually epsilon close to L if and only if there is some integer capital N greater than or equal to M, because sequence begin from M, if it is eventually close, there is some integer capital N bigger than M or equal to M even. After that, all the terms are epsilon close to L. That's what it says. We say that the sequence converges to L if and only if it is eventually epsilon close to L for every epsilon greater than 0. Let me write that also on the board. So we say that the sequence A converges to L. We say that the sequence AN according to Emmanuel Martin converges to L if equals if and only if anyway for every epsilon greater than 0 there is an integer capital F such that for each greater than capital N, A minus L less than epsilon. According to him, less than or equal.
Sir, that should be N. Okay. There exists integer.
There is an integer inside in just that written greater than N. Thank you. A minus L less than epsilon. So right away then we say that the sequence AN does not converge to L. If
There exists epsilon greater than 0.
there exists so epsilon 0 greater than 0 say such that
For all N,
for all N belongs to Z plus
plus there exists N greater than capital N.
at least little N greater than capital N
Such that
such that
modules of A n minus N strictly greater than
very good. So up to that level, very good, no? Up to that level, very good. But that's also something. That is something you can achieve. So if you draw a picture, what it means is now there is a difference between Cauchy sequence and this one. Cauchy sequence, according to the definition, you don't know where this epsilon radius, epsilon, no? I always epsilon and epsilon. This way, oh, is that how they spell epsilon?
don't know never.
This is like loan, you have borrowed some money. That's why.
Sri Lankan loans.
So the difference is here, you have this capital L line. So A in converges to L means you have 1, 2, 3, 4, 5, far away you go. These are integers. At the very beginning, and now you have this epsilon radius. You are putting epsilon pipe with epsilon infinite length and epsilon radius. This length is epsilon. This length is also epsilon. This little length. If the sequence converges to L, somewhere there is a point N. Before that, these terms are Buffalo, New York, downtown Florida, Badulla, Bandara, everywhere. But after this capital N, all the terms are bingo, inside the limits. No matter how small epsilon is, you always have a capital N. After that, all the terms are inside it. This echelon tube, I am sure this spelling is wrong. It's maybe LON echelon. Let's check it. I will check it and let's see. See, did you get the idea?
Yeah.
No matter, if you take an infinitely long echelon tube, if you put it around the L, you will not see because they are inside the tube. At the beginning, you may see 10 or 15 or 100 or 1000 or billion terms, but far away you will not see any term because they are inside the tube. It is not Cauchy means not, it does not convert to L means there is at least one tube like this. At least one tube like this of some radius, no matter which end you choose, after that it comes out of the pipe. That's the meaning of A. That's not converts to A. So you should try to prove very easy ones that converges. Anyway, so here he said, we say that sequence A converges to L if and only if it is eventually epsilon close to L. Eventually means for every real number epsilon greater than 0, for every real eventually close means after you choose epsilon there is an N. There is an integer capital N. After that all of them are at the epsilon distance at the most. Now one can unwrap all the definition here and write the concept of convergence more directly. See exercise 6.1.2. Let's see what it says. I cannot read. 6.1.2, what it says. Let A and be a sequence of real numbers and let L be a real number so that any converges if and only if given any real epsilon greater than 0, one can find n greater than or equal to m such that. So that's the same thing. The thing I told you, 6.1.2, nothing. Example 6.1.6, the sequence 0.99 is 0.1 close to 1, but it's not 0.01 close to 1 because of the first element. You understand that sort of thing, no? I should not spend time. Example, I went back. Proposition 6.17, uniqueness of limits. Let A and be a real sequence starting at some integer index m, and let L is not equal to L dash, be two distinct real numbers. Then it is not possible for A n to converge to L while also converging to L dash. In other words, it says limit is unique. From the picture it is very clear, no? Because if all the suppose this is L, suppose this is L, so no matter what epsilon you choose, far away all the terms are in that tube of epsilon radius. If it converges to L dash, then it must be in this one also. L dash one, far away. Far away terms are in this tube as well as terms are in this tube, cannot happen. So if you choose an epsilon like distance from here to here divided by 2, you get the contradiction right away. That's what maybe that is proof. Intuitively it must be clear to you first before writing the proof. he'll take not 2 but 3. 3 is better. Suppose for sake of contradiction that A was converging to both L and L dash. Let epsilon equals L minus L dash divided by 3. Note that, can you see when I read the proof, you don't know what is the first thing to do actually. Now when I am writing, I ask, now what should I do like that. Anyway, here he wants to get a contradiction, no? Then he has to choose some epsilon which will lead to a contradiction. So he is choosing epsilon. You can see from here it cannot happen. L minus L dash divided by 3. Note that epsilon is positive since L is not equal to L dash. Since A converges to L, we know that it is eventually epsilon close to L. Thus, there is a capital N such that dA in L less than or equal to epsilon after N. Capital N. Similarly, there is a capital M greater than or equal to M such that dA in L dash less than or equal to epsilon for all N greater than or equal to M. Now, he says in particular, we set simple N equals maximum of capital N and M. Then we have dA in L less than epsilon and dA in less than dA in L dash also less than or equal to epsilon. Hence, by the triangle inequality, we know L dash, you know the triangle inequality, no? So dL dash, he says, you can say it is less than or equal to dL AN plus dAN L dash. So that's how we get dL L dash less than or equal to 2 epsilon, which is 2 times L minus L dash divided by 3. So dL L dash is absolute value of L minus L dash, twice L minus L dash divided by 3, which contradicts the fact that L minus L dash is equal to 0. Understand the proof, no? Proof is clear. But it's not understanding, it's first thing is of course you need to understand. And you must be able to write the proof in your own, though it is a little thing. So that's how you become a mathematician, by writing. No, because otherwise we have many ideas, no? If you cannot write down, it is useless. Convergence and limits. Let's see. He says, note that we know limits are unique. Now we have proved that. We can set up notation to specify them. If a sequence A converges to some real number L, we say that A is convergent and that its limit is L, and we write. This is how we write. L equals limit A n tends to infinity. This is the way of writing. To denote this fact, if a sequence A n is not converging to L, any real number L, we say that the sequence is divergent. If when you are given a sequence A n, if it converges to some L, we say it is convergent. If it does not converge to any L, we say that it is divergent. Divergent means, so convergent means far away, close to something. Divergent means no matter where you go, it goes up and down here and there. That's the meaning. Not we write this thing. We say that the sequence is divergent and we have this undefined. I don't like that, but let's go along. Did you understand why do I say that I don't like it? Here is a divergent and we have undefined. When you write up to here when it converges and have a limit. Then you write after writing that undefined. I mean, nonsense, no? Okay, anyway, doesn't matter. The notation limit tends to infinity n does not give any indication about the starting index m of the sequence, but the starting index x irrelevant. it doesn't matter, you understand now, because limit is something far away thing. It doesn't matter from where it begins. Thus, in the rest of this discussion, we shall not be too careful as to where these sequences start, as we shall be mostly focused on their limits. So that goes without saying. We sometimes use the phrase an, we say an tends to x as n tends to infinity. By the way, we read like that. An tends to x. That arrow, that's how we read. An tends to x as n tends to infinity. It's an alternate way of writing the statement an converges to x. That's the way of writing. Bear in mind, though, that the individual statement a tends to x and n tends to infinity do not have any rigorous meaning. This phrase is just a convention, though of course a very suggestive one. I don't know why he wrote that. Let's see this one. The exact choice of letter used to denote the index, in this case n, is irrelevant. The phrase limit n tends to infinity n has exactly the same meaning as limit k tends to infinity ak. So that is redundant, the letter in right over there. For instance, sometimes it will be convenient to change the label of index to avoid conflicts of notation. If you have two sequences, better to have this one n tends to infinity, other one am. So no conflict. Sometimes having the same variable will give you a hard time. So I don't go through read the rest. Here we are going to do that. First limit we are proving, I guess, limit n tends to infinity, 1 over n is equal to 0. Actually, in other books, they prove limit of any constant sequence is the same thing. That's they prove in other books. Now you understand that? No, I discussed that for the whole sequence. Anyway, this proof is also very easy. But just because I say very easy, to you also may be very easy. But you have to see whether after closing the book you can write it. Because that's how no ideas come. To write the proof, you have to get ideas. Otherwise, what can you write? Nothing to be written. No? Yeah, anyway, so we are going to prove that limit of 1 over n is equal to 0. So I think you can prove this thing, because what you need to do is, without looking at the board, you have to prove that for every epsilon greater than 0, you can find a capital N, such that for each n greater than capital N, 1 over n minus 0, absolute value, less than epsilon. That's what you need to prove. So that's what he has done here. Let's see anyway. We have to show that the sequence an converges to 0, where an is equal to 1 over n. In other words, for every epsilon greater than 0, we need to show that the sequence an is eventually epsilon close to 0. So let epsilon greater than 0 be an arbitrary real number. We have to find capital N such that a minus 0 less than or equal to epsilon for every simple n greater than or equal to capital N. But if n greater than or equal to capital N, then absolute value of n minus 0 is, after all, 1 over n. It is definitely less than or equal to 1 over capital N, because simple n greater than or equal to capital N. Thus, if we pick n capital N greater than 1 over epsilon, we can do by Archimedean property. Archimedean is his principle, we call it Archimedean property, doesn't matter. Then 1 over n less than epsilon. And so an is epsilon close to 0. Thus an going to 1 to infinity is eventually close to 0, since epsilon was arbitrary. Do you understand the proof? So if we are writing the proof, we may not write all of them. Now this chapter is completely analysis. So you need to try to do very little things. Even the proofs in the book, I don't know whether you have time. You have not theory. From one hand, donuts. Then what is donut? Torus. From other hand, and here analysis. Over there, algebra, some statistics. I don't know whether you can manage time. But it is a very good thing to prove what is proved in the book without looking at that book. Whether you can write your own proof. So if you are writing your own proof, prove that. Limit 1 over n tends to infinity is equal to 0. Before you prove this thing, you have to have an idea. When you say limit of a sequence xn is L as n tends to infinity, what it means to you is that far away, here I capital. Far away, xn values are very close to A. Actually, more than that, you can make xn values as much as you please to n. You can make them close. So you have to have that idea. If someone says xn is close to L, what it means is you can make xn by making in large as close as you please to L, as much as you want. It may be 0.1, it may be 10 to the minus 2, it may be 10 to the minus 100,000. That close. You can make xn, distance between xn and A, at the most 10 to the minus 100,000. As much as you want. So you have to have that idea in your mind. When the limit is xn tends to L, far away, somewhere, xn values are, we say, arbitrarily close to A. Abhimata in single, Abhimata taram, close to A. And now here you can see, by intuition, when x gets bigger and bigger and bigger, 1 over n gets smaller and smaller and close to 0. You need to, that at the beginning that idea is important. But after, sooner or later you are going to prove and get limits to justify that you can say this way. But here, you know, when n gets bigger and bigger and bigger, 1 over gets smaller and smaller and get closer and closer to 0. So let's write the proof anyway. Proof. So, according to the definition, let epsilon greater than 0 must be the first line, no? Be arbitrary. Then, if you didn't look at the proof, you do your rough work. I always tell you, you do rough work somewhere. Then you need 1 over n minus 0. Absolute value, this is 1 over n. This must be less than or equal to epsilon after some capital N. But you know that 1 over simple n less than or equal to 1 over capital N, or since n greater than or equal to n, that n is something you are looking forward to. So if this is less than epsilon, then you know capital N must be greater than 1 over epsilon. So you prove that's the rough work. Then you write choose capital N belongs to Z plus such that n greater than 1 over epsilon by Archimedean principle. That's what he says. Archimedean principle. Now you have your capital N. Now you say let simple N greater than capital N. Then absolute value of 1 over n minus 0 is 1 over n, certainly less than 1 over capital N, certainly less than epsilon. This is the proof. You began with the epsilon, you did your rough work, what kind of capital N you need, you find out n must be greater than or equal to capital epsilon. You are asking yourself, does there exist a positive integer n such that n greater than 1 over epsilon? You are replying to yourself, yes, by Archimedean principle. Then you pick up and simple n greater than capital N. Then you get this, thus limit n tends to infinity, 1 over n is equal to 0. Right? Okay, now I'm looking at the book, but I should go. Proper convergent sequences are Cauchy. That is again trivial. Suppose that n is convergent sequence of real numbers, then n is also Cauchy sequence. Because R Cauchy means given any epsilon, you can find a capital N such that after capital N, any two terms are at a distance of at the most epsilon. That's the meaning of Cauchy. Now you have a sequence convergent. So if it is convergent, that means there is a real number. After some capital N, all the terms are at the most epsilon distance from capital N. And you can make that epsilon to be epsilon by 2. If all the terms are at the most epsilon by 2 distance from an minus a, all the an terms are at the most epsilon distance from capital N. If you take any two terms, then an minus L less than epsilon by 2 in absolute value, a minus L also less than epsilon by 2, then triangle inequality says a minus a less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. That's the proof. So no need to write the sequence 1 minus 1 etc. is not Cauchy sequence because it is not eventually unsteady and hence not a convergent sequence. Okay. For a converse to proportion 6.1 see theorem 6.4.18 below. What he says, suppose that Cauchy sequences are convergent sequences are Cauchy. Similarly, Cauchy sequences are convergent. That is a very, 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 very important. I said 4 times, no? Very important result. Yeah, that is, we call it completeness. So we need to be able to prove it, but we come later. But already it is good to know the sequence is Cauchy if and only if it is convergent. That is the result. Proving this side is very easy. Now I told you the proof. Proving the other side, I can tell you now, but you will not understand if I tell you just by the statements without writing. Okay, now we show that formal limits can be superseded by actual limits. Just as formal subtraction was superseded by actual subtraction when constructing the integers, and formal division superseded by actual division when constructing the rational numbers. Okay. Formal limits are genuine limits. Suppose that an is a co-sequence of real numbers, then an going on to infinity converges to lim an, that is lim an is equal to lim an. So here But actually, formal limit was constructed so that this is true. So let's see 6.1.6, what it says. 6.1.6. Okay, so it's kind of a little long. So I will leave it to you. If you cannot do, of course, I have to do, but I am sure you can do it. But this is an important result. Formal limit and actual limit are the same, but it's not as obvious as the formal division, formal subtraction, formal, whatever. Bounded sequence. The sequence of real numbers is bounded by a real number, capital M, if and only if we have a less than or equal to m for all n greater than or equal to m. We say that a is bounded if it is bounded by m for some number m. Some number m. Something I cannot believe about this book is that in any analysis book in the world, at the very beginning, they draw pictures to give the students some idea. In this book, no drawing at all. So, sequence is bounded means there is some number capital M, here is capital M is positive, here is minus m. So 1, 2, 3, 4, 5, 6. All the points are in between these two lines. Bounded means that any value is, that's no matter it says, the sequence of real numbers is bounded by a real number m, if and only if you take the graph of an lies between capital M and minus m, bounded. It's bounded by this. Then you can understand the sequence. I'm sure you can answer this one now. Sequence A is, by the way, here we say that the sequence is bounded if and only it is bounded by some number m. Bounded by capital M means all the values are in between minus m and plus m. This bounded means it is bounded by some m. So the sequence A is not bounded means then the sequence A is not bounded if what? Put our
for all real number.
if for all
For all m
greater than 0,
greater than 0,
comma,
there exists an
there is plus n, no?
there exists n
Below you said plus such that
mod an
is strictly greater than
m.
n. Not bounded means then no matter what m you choose, m and minus m, this is m, this is minus m, you have n here somewhere. A n is either here or here. Not bounded means that. Now up to that level, no, good. No, that's a very big growth. But now, however, now sooner or later, next chapter, continuity. So you get this statements, O every epsilon, there is a delta for each x such that now here only 1 or 2 quantifiers, no, then it goes to 3. Okay, now I'm going to the book. Very good, Putta, you answered well. So now we know the meaning of bounded. this definition is consistent with whatever we call from whatever every co-sequence of rational numbers is bounded, and inspection of the proof of that lemma shows that the same argument works for real numbers. Every co-sequence of real numbers is bounded. We know that, no? In particular, from proportional listing, we see every convergent sequence of real numbers is bounded. You can prove it very easily. What's the proof from in your head?
Every convergent series is a Cauchy sequence, and Cauchy sequence are bounded.
Therefore, this is bounded. The sequence 1, 2, 3, 4, 5 is not bounded and hence is not convergent. If it is convergent, then it is bounded. If it is not bounded, then it is not convergent, right? We can now prove the usual limit laws. Okay. Let A and B and be convergent sequences of real numbers. Let x, y be the real numbers such that x equals lim A n, y equals lim B n. Then he says limit of a n plus b n is x plus y. So actually limit of a n plus b n is limit a n plus limit b n. Limit of an addition is addition of the limits. Limit of a product is product of the limits. Limit of constant times constant multiple is constant times limit. Limit of a difference is difference of limits. Am I going backward? Because my finger goes up. And here is, suppose that y not equal to 0 and that bn not equal to 0 for all n greater than or equal to m, then the sequence bn inverse converges to y inverse. Okay, if bn goes to L and if L not equal to 0, 1 over bn goes to 1 over L. That's what it says. Then he says, suppose y not equal to 0 and bn not equal to 0 for all n greater than or equal to m. If an converges to an over bn converges to limit of an over limit of bn, they behave the way we expect. The sequence maximum of if a and bn converges, maximum of a and bn also converges to maximum of x and y. In other words, limit n tends to infinity max a and bn is max lim a n lim bn. The sequence mean a and bn also the same way. Mean a and bn goes to mean lim a n and lim bn. So in that all this is limits behave very nicely, very well behaved limits.
So can you give me some examples for G and H?
G and H?
Yeah.
Of course. I mean, it is by giving an example. What? Okay. Something I did not know. You asked some example.
Yeah, for G and
I mean, it is true for any sequence.
no, because up to F we use those laws and we
That's what you mean. Say, suppose you give me any, it has a limit. For instance, 1 over n. Let a is equal to 1 over n. So which n belongs to it? Let bn is equal to minus 1 to the n 1 over n. origin belongs here. Limit of, however, you need different
Yeah.
limits.
Yeah. How about n over 1 plus n?
No, because if it is, I'm sorry, you said what?
N over 1 plus n.
N over 1 plus n. However, if you say this is Vn, what will happen is that 1 over n is strictly less than 1 over Vn either. A. Again, 1 over n. And is it less than, no. Result is true anyway.
Yeah.
An is 1 over n, Vn is 2. So, I mean, if you say like this, since 1 over n less than, anyway, this one converges to 1. This one converges to 0. Then if you, since 1 over n less than n over n plus 1, right? Is this true? This is true, no? Origin belongs to n. Yes or no?
There's a range.
Origin greater than 1, no? Not for origin belongs to n. Origin greater than 1. Maximum of, how does he write? Max A, max according to him, A comma Vn. If n is equal to 1, n equals 1, max A and Bn, n samana ekedi, A n uiloku. A ek, natang A n, this is equal to 1 over 1, anit ewa Bn. No Bn, when n greater than 1, this one is big. So the sequence is, this sequence is, max A and Bn is first term is 1 if n is equal to 1. Then other, when n greater than 1, n over n plus 1. This is the max. So limit of this thing is, limit of n tends to infinity. Max A and Bn is, limit of the sequence is 1. First term is only 1, other terms limit is 1. And limit max of, not he writes, I should write the way he writes. Max lim An lim Bn n tends to infinity is equal to max lim An is 0, this one is 1, so 1. Right? Last one. Okay, so these results you should prove them. It's very important because now, I mean, after this chapter is your first analysis lecture like that. Whole bunch of things. However, there are 10 exercises. So I give 20 problems, no? So what I will do hereafter is I will follow his advice. Half of the questions from chapter 6, the other half is from previous chapters to get together. I can do some problems, but I think if it is a very necessary problem, I should do. Otherwise, you won't learn. No, taking down solutions won't make you a good student. I mean. Okay, so anyways, can you do not theory, donuts, and so many things? You don't say these things to Dr. Prabha, do you? The extended real number system, okay. There are some sequences which do not converge to any real number. Some sequences which do not converge to any real number, but instead seem to be wanting to converge to plus infinity or minus infinity. Like minus n, it goes all the way, all the time. I mean, we think some student would like to say that it is converging to minus infinity. But infinity is not a real number, no, there is nothing like that. For instance, it seems intuitive that the sequence 1, 2, 3, 4, 5 should be converging to plus infinity. That's how one would think at the beginning, while minus 1, minus 2, minus 3 should be converging to minus infinity. Meanwhile, the sequence 1 minus 1, 1 minus 1 does not converge to anything. However, does not seem to be converging to anything, although we shall see later that it does have plus 1 and minus 1 as limit points. We are going to learn some other word, limit points. Here we are learning limits. Limit points is another word about sequence. Similarly, the sequence 1 minus 2, 3 minus 4, 5 minus 6 does not converge to any real number and also does not appear to be converging to plus infinity or converging to minus infinity. To make this precise, we need to talk about something called extended real number system. We are going to extend the real number system. The extended real number system R star is the real line R with two additional elements attached called plus infinity and minus infinity. You add, if you draw the line minus infinity to plus infinity, for instance, to this end you attach plus infinity, to the other end you attach minus infinity. There are sometimes you bend this thing after this, not the nut person, this donut person. They have a way of, you take the real line, you bend and connect here. Then only one point. So you see what I'm saying? You understand, no? I mean, like here, and you say, if this is the real line, you bend it and this is another way. But here is different. To one end he is attaching plus infinity, to the other end minus infinity. In complex analysis, when you learn, you take the complex plane, this is the plane, you bend all of them to one point and make a sphere. That is another thing. So, whole bunch of things I should not talk about complex plane because you haven't started in complex numbers yet. Okay, so where am I? These state elements are distinct from each other and also distinct from every real number. an extended real number x is called finite if and only if it is a real number. You understand that? No, and infinite if it is equal to plus infinity or minus infinity. That is clear, no? This definition is not directly related to the notion of finite and infinite sets in section 3.6, though it is of course similar in spirit. Finite sets and infinite sets are different from this, but of course there is some relation. These new symbols plus infinity and minus infinity at present do not have much meaning, since we have no operations to manipulate them other than the equality and inequality. Now we place a few operations on the extended real number system. The negation of extended reals. The operation of negation x2 minus x on R, we now extend to R star by defining minus plus infinity is minus infinity, minus minus infinity is plus infinity. So this is by definition. Thus every extended real number x has a negation. Every, and minus minus x is always equal to x for real numbers. No? Then we are going to the definition 6.2.3. I guess we should not continue because it is related to infinity. No? We should start. It's slow. And next day will be very important. We are going to lim sup, lim inf, and limit points. Very, very important words in analysis. Lim sup, lim inf. So now we have to think anyway. Now next day, then I will assign 10 problems from chapter 6 and other 10 from previous chapters. We should try to catch up. No, you must be now. When I asked you about SUP this morning, you have been struggling to solve problems from the previous chapters. I am talking about SUP. This Putta may be thinking about chicken soup that he had at Badulla or somewhere, Horton Plain. So we should try to catch up. Let's see after 1 or 2 weeks whether we will be able to catch up, because we need to. Now you all are good at logical part. I guess you guys are good, very good, I think. But writing proofs is still not that comfortable because you haven't written proofs. No, this is proofs. That's the reason. So let's see next day. Okay, thank you.